Hello. Hello. BGM off. Yeah, good. Okay. I may be making a mistake doing this today, because I have a bit of a sore neck. But hey, if you see me twinge a little bit and sort of tilt to the right a little bit, it's because it hurts a little bit. Like there, I need a massage. Anyway, never mind that. As you may remember where we left off from this, I was building the 6502, and this is where we were. Why isn't it working? Hello? Is this the right one? It apparently is, but apparently it's broken. Excuse me. What the fuck? Oh, fuck. Oh, fuck. Oh, wait, we back? We back. Okay, we back. Except for the fact that the fucking picture quality is fucked again. Uncheck that. Ding. There. Done. Okay, picture quality is fixed. We had this. I did, before I started, actually completely rewire this. Why? It's pretty simple. I had to try and make it so this is a bit more accessible. I also had to get these plugged back in so that we have the thing that's plugged into it, this thing, which is the Arduino, connected. Which also, I've totally forgotten to connect that up. Could be bad. So let's just make sure that's connected correctly. And preferably not around my mouse. There we go. Common ground. That's sorted. Oh, I could even stretch the cable out and move it. Say, for instance, there. Either way, it's a common ground, and you know what? No, let's go over there. Just to be a dick. Just to cross the wires a bit more. Anyway, so we got our data lines. Data lines. Actually, they're address lines. Address lines, and then these are data lines. This little bundle here is data lines. And these are address lines. And that leads us to having... Well, if I switch this over to running mode, and then switch over to this, you can see it's constantly just, whoops, just outputting numbers and counting up in binary. It's beautiful, and it does absolutely nothing, because EA is the thing to say do nothing. It is literally just a command to say do nothing. So yes, let's just pause that. With my clock, I can also increment it. As you can see there, I can press a button, it'll increment. And the code is essentially just this. Yes, I don't care that you can see my name there. My real name there. My real name is not actually a secret. It's just, I prefer people go my in-game name. Just because it's nicer. It makes me feel a little bit more comfortable. Anyway, so this was the video we were watching. We were around about 15 and a half minutes. I've rewinded it back to 15 just so we can catch up.
And then when it reads from FFFD, it's getting an 8-0. So now
Okay, let's go a bit back further.
on the next clock cycle, through the first 7 clock cycles to initialize
First
it.
7 clock cycles is initialization.
And then on the next clock cycle, we can see when it reads from FFFC, it's getting a 0-0. And then when it reads from FFFD, it's getting an 8-0. So now on the next step, it should go to address 8000.
Yep.
And there it goes. It goes to address 8000. And of course, it's reading an EA there because that's what the rest of the EEPROM is filled with. And of course, if it's just going to keep reading those EAs like before. Cool. So now let's try writing a program that does something a little more interesting than just a bunch of no-ops. because at this point, the
Okay,
processor
cool.
is going to try and execute any instructions that it finds, starting at that address 8000, which is really address 0 of the ROM. So let's try feeding it some different instructions. Well, if we look at the datasheet for the microprocessor, it's got this table that shows us all the different options.
I have this datasheet, which might make it easy for you to see, but you can sort of see the register and all sorts of things like that.
And so, for example, if we want to do a load A, flip over here, we can find...
This is the internals of a computer. The basic computer that I run to do streaming and everything like that is based off of this. That's not a lie. We go to the microprocessor. I'll see if I can't find that myself. It's not that one. That looks like it could be it. Yeah, load A. B2. And no-op and NOP is do nothing. And that would be EA, which if we go here, EA. There, no-op. And so that's just it. I'm going to zoom in for you guys to be able to read that. So there's no-op. That's the command we're running everywhere. And he's talking about the load A command, which is LDA or LDA or LDA or... There's a bunch of different ones there that mean load A. As to exactly which one we need, I am very unsure, but I know it means... It could be A1, for instance. It could be Aura. No, it could be B2. It could be... Oh, wait, no, that's load Y. I don't know what LDY means, but LDA. Oh, it could be A5, for instance. I don't know. I do not know what they mean. It could also just be these ones here. LDA, which is AD. There's a million different load A instructions. Oh, there's one also there. BE. I'm guessing these are like parameters. I'm not 100% sure. AY. ZP. ZPY. Yeah, I can't say what it means. The instructions are hard.
Find this LDA instruction, which is going to load some value into the A register.
Okay, can I find that specific sheet instead of looking at these addresses? Is there a proper, like... Here it is. Okay, yeah. So you can see there's all these different ones. MA, LDA. There we go. We're looking at these. LDA.
And we can look here to see what the hexadecimal opcode is for that load A instruction. And there are actually a number of different opcodes for load A, depending on what we want to load into the A register. So, for example, if we want to load the A register with a value for memory, the opcode is AD in hex, and then we'd give it a memory address to load from. Or if we wanted to load from some memory address plus an offset, from the X or Y register, there are opcodes for that and other things. Or if we want to just load the A register with a particular immediate value, there's an opcode for that, and that's what A9 is. A9. So if we go back to where we're creating our...
But that's what that is. There's an A9, which is... A9, yeah, it's still A9. Nothing changed. I've got it right there.
Image file. If we set the first byte in our ROM...
Okay, let's grab this one. Bring this to the bit 2, and I want it on the right side because I think that's better. I wish I could expand this. Actually, hold on. Bye. Okay. Try a different terminal. Let's try XFCE terminal. Maybe that'll work. CD. What was it? Documents code 6502 code. All right, cat. Yeah. All right. Can I make this bigger now? View, zoom in, Control++. Okay, cool. This isn't working. Why isn't Control++ working? Is it Control++? That's what it says. Oh, wait. Is it this? Ah. There we go. All right, we'll do it about that size. I think that's maybe one more. Yeah, there we go. And I will move myself to the bottom left. There we go. All right. So now if we go Vim, make ROM. There, beautiful.
A9. This says load the next byte from ROM into the A register. So then we can set the next byte at location 1 here to, some other random value. Let's just say 42 hex. And then now these first 2 bytes here make up the first instruction that the processor is going to execute. And it says load the value 42 into the A register. And, maybe that's not very exciting. But now that we have a value in the A register, we can do something with it. Like, try writing it to some other address. So if we look back at our instruction opcodes, go down here, there's a store A instruction down here at the bottom, which will store the value in the A register.
All right, so let me do this. Let me do this. All right. What the fuck is a... I have totally forgotten. Hold on. Python comment. How do I do a comment in Python? I've forgotten how to do fucking comments. It's been so long since I've done Python. I've forgotten what comments look like. Hash. Oh, it's the hash. Okay. Okay. Let's just go. There. All right.
And again, there are different addressing modes, but this first one, 8D, is going to store the value in the A register to an address. So if we go back to our program, after loading the A register with this, value 42, if we add another instruction, 8D, that's going to store that value, that 42, somewhere in memory, and it expects the next 2 bytes here to give it an address. So we can set the next 2 bytes to, say 00 and say 60. Then, these 3 bytes together, the 8D0060, say to store the contents of the A register at address 6000. So what is this actually going to do? Well, let's give it a try. So I'll save this, and then I'll run the Python script to regenerate the ROM file. And now if we look at the hex dump for the ROM file, we can see our program here at the beginning. So this is our program, the load A42 and then the store A 6000. And then everything else is full of EA instructions up here till the very end where we have the reset vector, which tells it to start executing, right here at the start. Okay, so now let me just power this off and I'll fish the EEPROM out of here so we can reprogram it. Get that back into the programmer. And then I'll go ahead and reprogram it.
Okay, I'm going to figure out what the fuck my freaking mini-pro command was for this. Or maybe I don't need to. I don't know. I'm fairly sure I do, though. I need to... Let me just back to this so I can show you how I get this out. This is how I get this out. Go like that. Pull that off. Pull that out. And there, it's gone. Alright. And then, so this is the programmer. In order to get this on, sorry it's a bit blurry because everything's a little bit closer. Just move this out the way. See that there? There's the icon. So I need the little dip. There. Goes there. And that needs to be opened. See, it falls straight in. Close it down. That won't come out. Okay. Now let's disconnect the Arduino and actually let's disconnect the system first because it's probably getting confused. Arduino disconnected. So I can use this cable, turn around, and plug her in. Done. Okay. Now we have a random thing. Alright, let me just double check to see how I fucking load this shit. Do I have a history for this? No, I don't. I do not have a history for this. You know what I should really do? Vim flash.sh. I'm gonna make a short script that allow me to flash this. Alright, hash exclamation slash bin slash bash. Alright. Hey Death, how's it going? Now I gotta remember how to load this damn thing. Oh fuck. Where was the bit about the programmer? I don't have it in here, do I? No. The T48 programmer. Oh, wait, hold on. Wasn't it? Man, Mini Pro? Yeah, there it is. What are we making? What are we writing? I just want to make sure this is easy to flash. Alright, so... Okay. What was he writing first? Let me double check to see what his command was. Mini Pro dash P AT28 C256. That's still the same. P is just that. And that should be listed down here somewhere. I'm just trying to make sure. Yep, P. Okay. Dash W. And then I'm going to go $1 for the dash W. You know what $1 does in Alright, yeah, I'm great. I do have a bit of sore neck, but apart from that, I'm good. That's my minor complaint about today. At least it's not so sore that it's actually affecting my chest. That was weird yesterday, but it's not anymore, so hey. There was another thing I needed to do to make sure that it doesn't lock or unlock. It was what was it? It was U and P. Yeah. There it is. And so yeah, so it was dash UP. I'm fairly sure that's all it was. Okay. I'm going to do that. All right. Now let's see. Alright, chmod plus x flash. Alright, /flash. And what was I doing? ROM minpro. Of course, I can't fucking type. Mini Pro, please. Alright. Is it gonna work? Is it gonna work? Seems to be. Okay, cool. It's done. It's written. For it is written.
Writing that new ROM file. There it goes.
My difference is he's doing write protect and he's not doing write protect and I have no choice to, but because the T48 is weird. Okay, got my little chip, taking it out. That's not right. Get rid of this. Brilliant. Actually, let's just plug this thing back into the Arduino. It will be getting garbage data for a little bit. Especially considering there's nothing enabled. Alright, we now gotta put this back in. If it goes that way. Yeah. Oh god, the wires are in the way. Get out of the way, honey. Eh? Is that correct? That looks correct. There. It's in. Yep. That's in. Alright. Now, I didn't check to see whether I could hex dump the ROM first. Let's run a hex dump on the ROM. Yeah, so there's bits and pieces. There's a weird there's this stuff here. That's the new part of the ROM. Alright, let's get back to the Vim. The original make ROM. And that's what we've done. Alright, you can't even see, but yeah. There. So there's what we've done there on the right side there. If that's still not good enough, I'll get rid of this. And I will go Control Plus. There, now you'll be able to see even better. Actually, Control Plus. There you go. Now you'll really be able to see. I wish I could do that for this. The serial monitor sucks. I wonder if there's a way of TTAMCO. Hold on. Access serial device line. Read serial device command line. Linux. So I'm just gonna look this up real quick. Because I would rather read this from the command line. Oh, cool. E dev slash tt. Oh wait, no. Let's get rid of this and go. I use that command line. I'm gonna use the other one for this. The XFCE terminal. There we go. Then we'll. There we go. Now we'll be able to do that. And I'll be able to get rid of this serial monitor. Actually, hold on. I probably shouldn't have gotten rid of that straight away. Serial monitor is dev tty acmo. Okay, so stty-f /dev /tty acmo. ACMO. All right. ACMO and hold on, what was it again? 57,600 is the speed. Speed. Oh, hang on. I could just do this. Do I have screen? No, alright. Sudo pacman-s screen. Whee! Alright, screen /dev /ttyacmo. And it's 57,600. That did not work. Apparently that doesn't work. Okay. What if we just cat /dev /ttyacmo and we put 57,600? No, device or resource busy. What if we close down this? No. So what if we Windows C? All right. Is this going to give me something? There's a button. No. No, it is not. Why doesn't this fucking work? Can I just hold on? Cat. Oh shoot, I've lost one. One of my wires broke. Get back in there, bitch. Here is that. That's fine. That's fine. Okay, so this don't work either. Okay, apparently neither of those don't work either. Let's just try this. Dev /ttyacmo. Speed 57,600. CS. What is STTY? Okay. Dash A? What the fuck? Arduino, how do I do this? Oh, okay. I see. Why isn't this working? Oh. This might actually explain why. There we go. Alright, you know what? If I can run the Arduino IDE at the same time, I will. There we go. Okay. Now if we stop this, it'll stop. And I can blink it, and it works. So now if I reset it, and
Put the EEPROM back in our circuit, and I'll power it up.
all right, let's. We powered it up. That's the problem I was having before. All right. Can you kill the serial monitor, please? Yeah. And now it does that. Okay. All right. There we go. All right. So 1, 2, 3, 4, 5, 6, 6. There we go. Whatever. All right. Here we go. It's about to start. It's now reading 080.
And then just to get this reset and everything, I'll let the clock run a little bit and then hold down reset to reset it while the clock is running and then stop the clock.
Yeah, I probably should have done that instead. But no. It's definitely, I think, A942. But then it's writing 8D80. That's some new shit. You don't see write very often. 6042 EA. Yeah, it's reading now. Oh, wow. It was writing for a moment there. I think the read-write pin's fucked. I don't know why, but it's just... It's getting write commands constantly when it probably shouldn't be. And now it's just constant write pins. What? Is this right? What is wrong with that? Do I have that in the right plug? Hold on. I've got the clock in the correct one. But do I have the frickin' right pin in the right pin? Because I feel like that's wrong. Alright, let me find this. Where is this? Alright, RWB is 35, so... Let me get my thing out. And let me just... figure this one out. Alright, where's my fucking... I've lost my needle nose. Oh, there they are. It's gonna be a bit difficult, but I need to see this, so... Reset button. You probably can't see what I'm doing here because, well, let me just say that. Yeah, reset button. FIO2. Whatever the fuck FIO2 is. SOB. What a sub story that is. FI2, or clock, otherwise known as. NC. No, BE. BE. NC RWB. Okay, yeah. We've got the right button. Right, the wrong plug. Pull that one out. Plug that one. And we'll just hold that. Let it run. Switch everything until I can switch it back. Oh, where the fuck's the button? Bottom right. Alright. There we go. Getting some 801Cs. Switch that off. Release. Alright, 1, 2. Alright, there we go. We've restarted. 3. Yeah, now it's reading. Alright, I'm seeing 801, 802, so it has read. A9. And there's the right, 60442. Which is exactly, if we go back to this one, 6000. I'm pretty sure that's what that would be. 6000, yeah. So 6000, it's writing 42. So it read 42 into the buffer there. And then it did some weird stuff. And then it did 42. And then it jumped to where it needed to go, which is 0060. Which is exactly where, well, whatever. It went to the right spot, though. Which is good. So now it's writing to address. If we press thing, it jumps to 805. So the stuff from 8000s where it's doing the stuff, it tried to write that to 6000, and then it went to 8005. And now it's just going to do that forever, because that's all that's left. Okay. Cool. We've got that sorted.
And then I'll go ahead and clear the output over here so we can see what's going on. And then I'll start stepping the clock.
Let's verify
again,
what I just
7
saw.
clock cycles to initialize.
I'm not doing that because I don't have the right friggin'...
And so we see it's reading 00, then 80. So it's
jump
jump
booster
to
thing,
8000.
whatever the fuck it is.
And there it goes. And now you can see it's reading A9.
He has a capacitor over the button. Yeah, he does. He has a capacitor over the button. What does he have that?
Is that my debouncing problem right there?
I reckon that is.
I reckon the capacitor over the button's the bit I'm missing. Much random ones. I'm gonna take one from this little thing. I'm gonna add this capacitor and put it over the button because, well, he's got that there and I don't, and I'm wondering if that's my problem. Because I don't ever remember seeing a capacitor over the button until I'm looking at that, and now I want it because I'm hoping it'll debounce me a little bit better. Let's just. I don't think I need much. I think I've already got the gap. Alright, that seems to have... Alright, we'll take that out. Okay. We just put this back in here. We're modifying this. We now have a capacitor over there, and that was a bit awkward. All right, I wonder if that's gonna stop the bouncing, because I have been having bouncing problems with that damn button. Can I actually get some good outputs? Let's see. All right, let me try it. we go here. It's not perfect. I can still bounce it, but I almost think that that's the button, not the thing. But it is way better. Oh, yeah, that's so much nicer. All right. Yep. Cool. Nice. All right. All right, reset. All right. Cool. Okay. And then 1, 2, 3, 4, 5, 6, 7. All right, there we go. And that's the startup sequence done. As you can see, it's reading from 801. Does that. It's read 42 there. That was clearly the value we wanted. Keep in mind, that's hexadecimal, so that's not actually 42 in the non-binary sense, but in the binary sense, it's 42. And yeah, so it's written, and then it goes. Awesome. Now we don't have bouncing problems. I can't believe I didn't realize that.
And of course, that's the... There it goes.
Sick.
And now you can see it's reading A9 from address 8000. And of course, that's the opcode for the load A instruction. And so next we'll see that it reads the 42 hex. So at this point, it should have loaded that 42 now into the A register.
Hell
next,
yeah.
We're going to see the instruction 8D, which is the instruction to store the contents of the A register.
Yep.
So then it's going to keep going to get the address to
saw
store
that.
to. So we see a 00 and then 60. And so
the
at this
next
point,
one
it's
is-
read this instruction to say, store A
Guess the next
address,
two parts.
6000, because right, it's going to read that
6000.
sort of backwards, or
Yeah, it reads that.
in little endian format, if you will. But now watch the next clock cycle. Now the processor set the address to 6000, and now it's writing to that address instead of reading.
Yep.
And it's writing the value 42. And then if we
The
keep
answer to the
going,
question
you
of
see
the
it
universe
jumps
right
back
there.
to address
Oh, boy.
8005.
And then it just
And now it's just going to
continue.
read, the EA no op instructions, since that's what the rest of the ROM is filled with. But this
Yep.
is pretty interesting here. We got the processor to actually write this value, which means it set all the address lines to 6000, and then the processor put the value 42 on the data lines and set the read-write line low to indicate that it was writing. So in all these other cases, when we look at the data here, this data is coming from the EEPROM, right? This is our program that we put in the EEPROM. But this 42 here, this is actually being put out on the bus by the processor itself. Now in this case, there's nothing actually at address 6000. The only thing connected to the processor, other than the Arduino,
Woo,
that we're
lad.
just using for monitoring, the only other thing connected is the EEPROM, and it's only enabled for addresses 8000 through FFFF. So in some sense, when the processor outputs to address 6000 here, it's just kind of yelling into the void. There's
Yep.
nothing actually paying attention to address 6000. But, we could add some other hardware that responds to different addresses.
Hell
Either
yeah, new
RAM,
hardware.
So, data like this 42 could be stored in memory somewhere, or other hardware. In fact, this is actually how we're going to do input and output. So if we want to output data, we just have some hardware that responds when the processor sets the address lines to a particular address like this.
I've just seen
And
what's
then
ahead.
from the processor's perspective, it'll just store different values to a particular address to tell the output hardware what to do. So let's think about what that output hardware might look like. So if our program and the processor
Could you
is
imagine
going to output
a computer
data,
program that just well, this is that computer program, but that used in production that just writes 42 to that one address and that's it.
by
It's
writing
just-
to a
yeah.
particular address, like this writing to address 6000, for
That's the
example,
only thing
then
it
the output
does.
hardware, whether it's a display,
Does
or
it and
whatever
then
it is,
stops.
it needs to be
And
able
that's
to look
all
at the
it ever
address
does.
lines of
Does
the
it
processor
once
to
and
see when
stops.
they match, this particular address. And then when they do, grab the data from the data lines here and do something with it. And, the important insight here is that when the processor outputs data, it's using the same address bus and the same data bus that it uses for everything else.
Yep.
Some processors might have separate interfaces or something to do I/O. But the 6502 uses the same address bus and the same data bus that it uses to fetch and execute instructions or access memory or whatever else. So if we're thinking about how output hardware might work, then we've got to realize that these address lines are going to be flipping all over the place.
Indeed
And the
they
data lines
are.
are flipping all over the place. And so the only thing that's relevant to the output hardware in all of this is this one moment here where the processor is actually using the address and data lines to output something. So if we wanted some sort of output display to display this 42 or whatever, then we'd need some hardware that's looking at the address lines, and then only when they match 6000, grab the data, this 42, and
Okay, I
latch
think
it.
I know what's going to come next. We're going to build this
into an
hardware out so that we have a little screen that we can deploy to.
Journal register or something. Somehow store this for you too,
Can't wait for that.
because it's only there for this one clock cycle. So
I
this
do
means
have
any
the
kind of
screen.
output device we need has to have at least two components. Some address decode logic to detect when the processor is writing to this 6000 address, and then a latch to store the data that's output so that it can be displayed even after the processor here has moved on to other things. Now, when it comes to latching data, I've got a whole series of videos where I build a CPU from scratch. And as part of that series, I've got videos where I talk about SR latches, D latches, D flip-flops, and then how to build
I
a
may
register,
do that one
and even an
eventually, but
output
that's going to
display,
take
all
forever.
from scratch.
And it's
So if you want to go down
more
that rabbit
complex
hole,
than this
well,
one.
you're in luck. But for
Like,
this video,
that's building
I'm
a
gonna use
computer,
chip that does a
CPU
lot
and
of that
all.
work for us. And that's the
in a bunch
65C22
of breadboards.
versatile interface adapter. And as the name would imply, the 65C22 versatile interface adapter
65C22. I have that. Where did I put that? No, seriously, where did I put that? Is that me? That might be it there. A bunch of stuff here. Okay. Disconnect the power. And disconnect the. Actually, we'll leave that. We'll leave the that there. Which one do we have? $65C22. I have it right here. It's the longest chip aside from the actual. It's about as long as the 6502. So you might notice these are all 65C something.
65C02 microprocessor that we've already been using. And it does a whole bunch of interesting and useful things that would take multiple videos to fully explore.
Hell yeah!
But one of the most basic things it does is latch data for input and output. So if we start by just looking at the pinout, you can get some sense of what it'll do for us. It's got these D0 through D7 pins, which interface right to our data bus. And it's also got the Phi2, which is the clock pin, which is designed to connect right up to the same system clock that we use for the microprocessor. And, the nice thing about this chip is because it's designed to work with the 6502 processor, all the timing is going to just work. So we just have to connect the same clock, and it's just designed to be able to send data back and forth on the data bus here. And, we could still go through all the timing diagrams and double check that it's actually going to work. But the point is the chips are designed to work together, so I'm not going to go through all that in this video. But it's got the clock, it's got the data, it's got a read-write pin that will connect right up to the read-write pin on the processor, and then a couple of chip select pins, the CS1 and CS2 here, that we can use to tell the chip when the processor is actually talking to it. And so we'll have to have some address decode logic that when we're writing to just the right address, it enables those chip select pins. And so basically once we hook this up, the processor is going to be able to easily talk back and forth to this chip. And then on the other side, there's just a whole bunch of I/O lines that are latched. So we've got port A 0 through 7, and then port B 0 through 7. And these are latched outputs, or we can actually also use them for inputs. And so one of the things that this chip lets us do is we can send some data from the processor over here, and then it'll latch that data onto one of these I/O ports over here, the port A or port B,
I'm just playing
and then
around.
hold that data there while the processor goes on to do other things. And then it's got these 4 register select pins, RS0 through RS3, that are used to select which port we're talking to, or some of the other functions that the chip supports. So we're going to hook up the clock, we're going to hook up the data bus, and we're going to hook up the read-write signal. But before we get to any of that, we need some logic to figure out when we're actually talking to this chip. So for example, if we want data that we're writing to address 6000 to be latched by the 6522, we need some logic to enable the 6522 when the processor is writing to or reading from address 6000. So for address 6000 hex, this is what that looks like in binary. So this is what the address lines will look like when the processor is writing to address 6000. So we need some logic that'll tell us if the address bits are set to these values, and then if they are, enable the chip select signals. And by enabling the chip select signals, that tells the 6522 that it's time to pay attention to the data bus. And the 6522 has actually 2 chip select signals, and they both have to be active. Chip select 1 is active high, and chip select 2 is active low, which is indicated with the bar over it. And actually, if you look at the data sheet,
Active
they don't
low
have
means
the bar,
always
they
on,
just have chip
active
select
high
1 and
means
chip
always
select 2B.
except for
But the B
alternate
at the end just means that chip select 2 bar, so there should be a bar over it. But I guess instead of drawing the bar, they just put the B at the end. But anyway, that's what that means. So like RWB is read and then write with a bar over it. like that. But in
Okay.
any event, I'll just draw it with the bar like that to indicate that it's an active low.
I'm still
So if
holding
we
this
wanna build
chip.
some logic that will recognize when the address bits
I'm
are
gonna
set
put it
this
in
way,
and probably that'll
and then
be it.
enable both of these chip select signals.
I don't know how much
Um,
time I got left, and I do want
Let's
to get
just
to bed
actually just
pretty.
start with the first
relatively early,
bits
'cause-
here. So if we just look at the first 2 bits, the first bit is a 0 and the second bit's a 1. So if we invert the 0 and then just take the 1 and then AND those together, well, that'll tell us that the first 2 bits are set correctly. And of course, we could actually build something similar with only NAND gates that would look like this, where here this top NAND gate is essentially inverting that 0, so
Yep,
just like the
that's what
inverter
we've
we
got
just saw.
here.
And then we're ANDing it with the 1, and then we get a 0 over here. And actually, we can feed that directly into the active low chip select 2. So chip select 2 here will be active when the first 2 bits of our address are right. Then what we can do is we can feed this third bit, address 13, in directly into the chip select 1, because that's supposed to be a 1 when our address is at 6000. And so that'll be active and check if the third bit of our address is a 1. And so just like this will activate the 6522 when the first 3 bits are correct for an address of 6000. But you might be wondering, what about the rest of the bits? How do we check if they're all zeros? Because the rest of these bits are all supposed to be zeros if the processor is writing to address 6000. Whoops. Well, it might seem strange, but I'm actually not going to check those other bits at all. I'm just
Which
going
is
to
a
ignore
bit
them.
weird.
So that means that this chip is actually going to be enabled for any address from 6000 all the way through 7FFF. Because those are the addresses from 6000 through 7FFF. Those are the addresses where those first 3 bits are 0, 1, 1. And I know what you're thinking. It seems horribly inefficient, right? Are we really taking up,
Yeah.
over 8,000
So
addresses
what we don't know
just
here
for
is
this one chip? It seems like
the
such a
reason that
waste,
first
right?
bit has
You
to
know,
be 0,
over 8.
right, is because it has to be 1 in order to read from the ROM. That's the 8,000, right? So 8,000 is onwards is ROM. I'm pretty sure. Which means we are
1,000
now
addresses
using the
just for this one
additional
chip.
bits
It seems
for
like such a
other stuff.
waste, right? But with engineering, everything is a trade-off. So there's never like a perfect design.
Yeah,
Because one factor that's always in play is cost. And a big advantage of this design is that it just uses these 2 NAND gates. And in fact, you might have already spotted that this NAND gate here is already in our circuit because we're using it for the chip enable for the EEPROM. So we can actually kind of use double duty on that. So really, this design is only adding a single NAND gate. So yes, we're kind of wasting 8,000 addresses or whatever it is
Yeah,
to
that's a bit of a
activate this
problem.
one chip. But we're actually saving a whole bunch of logic gates. Because if we had to put logic gates in here to check that all of these bits were zeros and feed that into some logic that activated the 6522, that would require a whole bunch of logic gates. And so, it's a trade-off
Would.
that ultimately depends
You'd
on
need a whole nother
exactly
fucking
what we're
board for
building this
that.
for. If we're trying to build something that requires, a certain number of addresses where we need, a certain amount of memory or a certain amount of I/O or something like that, we might have to add that complexity to use.
But you
our
can always
address
add
space most
more to, like,
efficiently.
for instance,
But
A12 to activate something else or something like that, and then you just add one gate to make it so that if A12 is 0, it disables this and enables something else, and so on and so forth.
If we don't actually need all of that address space, then maybe it makes more sense to accept something that, kind of at first sight might seem like we're wasting some resource like addresses, but really we're saving on the resource that really matters in our case, which would be logic gates. And that's hardware, which, if you're designing a product, that directly translates to cost. And, I suppose, yes, we're building this as a hobby or something, so you might not care about that, which, fair enough. But if you're interested in real world engineering, you're not always going to have the luxury of prioritizing your personal aesthetic of some ideal, quote unquote design. You're eventually going to have to make trade-offs like this. And one interesting factor of this design is if you wanted to add multiple 6522s, which, if you want to expand this, you might want to do, you could just use address 12, 11, 10, and so on, and hook those up to the chip select 1 pin of the second or third or fourth 6522.
Yeah.
So if you want to add more I/O, this design makes it kind of easy to expand. Still not efficient use of the address space, but very efficient use of the hardware because you don't
just
actually
need
need to
an
add any
invert of
additional address
CS
decode
for
logic.
A13.
But anyway, let's
The other
start
one, but
hooking
never
this
mind
up. I'll start by disconnecting the Arduino just so you can see what's going on in here.
Okay.
And I'll add the 65C22 chip here. And if we look back at the pinout here, you can see that power and ground are VDD and VSS, so pins 20 and 1. So I'll start by connecting those. So pin 20 is power, 5 volts, and then pin 1 is ground. If we start with that address
Okay,
decode,
let me do this. Get the initial startup. Let me just remove the Arduino completely. I might just leave it leave it disconnected but plugged in. Okay. Back to this. So we are here. And here's my little chip. Oh, it's not really that little, is it? Wow, he's going right next to the thing, isn't he? He's going like right here. Huh. Huh. Okay, that's where he's going. That's where that goes. Now I need power and ground. What have I done with my little bastards? I just want to get the power in and the ground in, at least. Oh, you fucker! Who was that? Ah! Why do I leave that so loud? Oh God, my ears. Oh, hey Jay. Sure. Where did I put the bottle? There it is. Down there. Can you give me a neck massage? Can you come down and catch a plane and give me a neck massage? A bit of a sore neck. Apart from that, I'm pretty good. Ah! Tasty. Okay. Now, I can mark that as complete now. Let's try not to tip shit everywhere. Let me find a... Do I not have one? The fuck? Okay, this is gonna be annoying. Oh well, I guess I'll just mess with one of these. So, if we do that, just straighten it out. Let me just close this as well to make sure we don't fuck it up. Okay. That's pin 1 from there. And where's my little cutter? Okay, we're gonna guess. How far is that? I think I'm gonna need about... No, hold on. We'll go... Just cut this bit here off. Most of it. Okay. Ah! Fuck, I lost it. Okay. Alright. And we just put that little bastard in there. And if it's not too long, which it definitely is, it will work. Fuck. It's alright. Trial and error is the best way of doing things. That was essentially cut twice, but who cares? They say measure once, cut twice. I cut too far and then I cut again, and it's fine. Well, measure once, cut once, or measure twice, cut once, sort of thing. But you know what? I cut, then measure, then cut again, because fuck you. That's why. Okay. Let's try that. Come on. Get in the hole. And that's what she said. Perfect. There we go. We got that one. Now for the red boy. Do I have one for the red boy that I don't need to worry about? It looks like I might actually. Hold on. Let me get it out. It's quite small. Oh yeah, look at that. Alright, this one goes on the other side, on this end. Here. Brilliant. There, done. That's all powered now. That one has power. It's excellent. You might notice I've got this spare board here, but that's because there's more to come. But otherwise, these two boards are going to be the basic start. Okay, cool. That's connected. Go back. Where's my thing?
Code
Pokey and you are
logic.
playing
can see
Ark?
that we've
Oh,
got
nice.
the chip select 1 and chip select
Well, I hope
2
you enjoy
will
that.
hook up to this logic here. And of course, we already have this NAND
I'm doing
gate
nerd
hooked up
shit,
here.
so
we've
you
got
know.
address 15 coming down. That's this green wire going into the 2 inputs of one of these NAND gates. And then the yellow wire is the output here that right now is going to chip select for the ROM. But we can also take that and bring it into another input for another NAND gate, because this chip here has 4 NAND gates on it. And that's actually why I used a NAND gate instead of an inverter here, since we can use one chip that has 4 NAND gates on it to do both things. So I'll connect the output of this NAND gate around to the input of another, or one of the inputs of another NAND gate on the same chip. So that's this connection here.
Oh boy, ain't that fun. Okay, I'm gonna use a yellow wire because that's what they're using. I may have to make a yellow wire, but hold on, this one might work. We'll check this one first and see if this one works. If I can get my freaking grubby little fingers on it. There we go. Alright, so he. I mean, it could be a he. She. Go there. I mean, I'm fairly sure it's he. Could be a they, but yeah, that's what they're going to do. All right. I'm hoping I can turn this around and do this, but no, I don't think so. That ain't gonna work. That ain't it, bro. That ain't it. That one ain't it at all. All right. Gonna need to make some wire. Okay, let's just have a guess about, say about there. Bendy boy. This one might actually be a bit long. Oh no, it's fine. Okay. I'll just do this. Yep. Man. That kind of worked quite well. Alright, where are we putting this? It looks like we're putting this on that one there, on the third pin across. Yep. Which means if you put it on the third pin across, you count another 3 pins deep. So about there. Fairly sure. And then I'm losing my thing. What she said. Don't mind me, my microphone's just floating up. Microphone isn't exactly stable from excessive move. Come back down. You better come back down now so I can kick your teeth in. Alright, I actually want to bend it like that. So I kind of did leave a bit of gap, but wow, that's fucked up. Alright, there we go. That's the wire we're aiming for. Into the wire we're aiming for on the 10. Yep. There. We have it in. That's in. And you can't see a thing. There. See, I got this green this wire here. What's next? I need to.
And then we'll connect address 14 to the other input of this NAND gate down here. So address 14 is one of these, is this address pin up here. So there we go. That's address 14.
Oh,
and that's
fuck.
come
What is he
around and
doing now? Did you just pull that out?
of this NAND gate down here. So address 14 is one of these, is this address pin up here. So there we go.
Oh, God. Oh, God. Wait, is that a...
So address
blue pin?
14 is one of these, is this address pin up here. So So there we go. That's address 14. And
That's the second one across. I can't fit that. I can't fit shit in there. I can't see shit. Hold on. Pull these to the side. I may have to move these up. All of them. All these lines. All right, time to do a bit of rewiring so I can see what I'm doing. All right. I'm going to leave those ones there because they're going across the CPU and that's going to be a pain in the ass to deal with. I am going to move these ones up one so I can actually try and, you know, at least see what I'm trying to attach to. Try and get rid of this, get this out of the way. It's going to make it incredibly difficult to deal with in the future, but hey, I'd rather have to. Oh god, that's dangerous. We may end up having some problems with like cross wires or something here. Oh, some of these are really fucking long. Like these go deep. Balls deep. Alright. Okay, they're in. I don't think there's any cross wires, but god, I hope not. Just press them in, make sure. Okay. This is the second one, so if I get the first one, I move that one back that way as well. Just a little bit more room. Yes. Matter of fact, I may have to do that with the second one as well. Wait, that's not already moved there, is it? No, it's not. And he's not disconnecting it either. Oh boy, that's fun not. Eh. There we go. It's been somewhat reorganized. It is an absolute fucking mess in comparison to his. But hey, I now have a green pin that I can access. I'm pretty sure it's the second one along. God forbid it's not the third one along. Looking at the video, it definitely is the second one along. Okay. That being the case, I'm going to do my long green boy. My long reel of green. My long reel of green. I don't know why it just changed color like that, but hey. Okay. I'm honestly tempted to go this way, but I'm not going to because I don't think I can. Okay, that's in. We can't. Stop doing that. No, that's come out. Oh, where was that? Oh, right. Pretty close. Obvious. There. Okay, this is the problem. So we're going to need to go that way. Right. Which is a huge problem. Because, you know. It is. Okay, we run that way. This is how I'm going to have to deal with it. Alright. Now, we can't. Let's just straighten that out until we can get it in there. Alright, now get in there, bro. Get underneath. Zap it under. You just bring this way. Can I? Haha! Okay, now we gotta get it around. Brilliant. All right. Okay. Excellent. Now, where's he plugging this thing into?
That's going to come around and connect to the second input.
Ugh, fuck. I actually want it to go this way. If I can't just grab that, go. Bring it this way. And grab this thing. Try and bring it that way. It's about as good as I'm gonna get. I'm not gonna try and get too. I think I'm trying too hard to make it look neat. So I'm just gonna use my grab and turn method like that. Just go like that and go, okay, so it's there, which means we need to cut it like there. Trim it off, and then break it down, and then put it in, I think it was that one. Yeah. There. That's all in. That's all good. No, I think in order to neaten this up, just going to grab the. Fuck off. Sorry about this. I need a better friggin' shock mount. Okay. There we go. Okay, so if we grab this, pull that and bring it there. We'll do the same for each one. We may be able to have a bit of a cleaner situation here. Provided we don't have crosstalk and cross wires. But hey, if we have that, who gives a shit? As long as I can fix it later. I may have to remake some of these wires, but hey. Why doesn't that want to go in? In you get. That's your hole now. Oh, it's your hole now. There. I think that's right. Let me just get my torch and double check that. Yep, that's correct. That's good. Okay. Now we actually have a little bit more space where we can deal with things. See, I can't do that because that just pops those out. Wow, that fucked everything up, didn't it? Oh wow, that really doesn't want to go back in. Hold on, where's my thing? You get back in there, please. Just because one thing didn't happen. There. Alright. Now I have that.
On this NAND gate. Then the output of this NAND gate is going to go to the chip select 2 input of the 6522. So the output of this NAND gate is this pin right here, and then that's going to come around to the chip select 2 pin.
Go back. You'll be able to see what I'm looking at.
Output of this NAND gate is this pin right here, and then that's...
Why is it that one? Oh, for fuck's sake. It's this one here, I'm pretty sure. You might notice I do a lot of the bending by hand. If I notice a kink in the wire, I just straighten it out with my freaking pliers. And I can just go bonk. A nonk. donk. Okay. Where are we putting this?
That's going to come around to the chip select 2 pin. Which if you look back at the pinout here, chip select 2 is pin 23. So that
Oh, fucking hell. All the way over here. This third pin along here, so. Bye. Jesus. It really doesn't like this. Well, let me just take this out and try and straighten this up. Yeah. Don't know whether that's going to make it better or worse or what. Definitely crush some of the insulation, but hoo-ha. Who cares? Alright. Third pin along, which is that one. Haha! Alright, we're going pop. We're popping off here. Alright, alright. Then there. Straighten it up. Get it nice and decent. Plug that one in. Plug that one in. Brilliant. Awesome. Look at that. Now this yellow wire.
That's this pin right here. So now the 6522 is only going to be enabled when address 15 is 0 and address 14 is 1, because that's what this logic does. Next, we can connect address 13 from the microprocessor over to the chip select 1 input of the 6522.
Which one's that?
So address 13 is also up here. It's starting to get a little bit tight, but let's see if I can get this in there.
Starting.
Address 13 is then going to come down and connect to...
I am so done here. How am I supposed to get that? There is legitimately not even a spot for it. I'm honestly surprised I got the other one. Which is this one. 13 is the one next to it. This one. I can't even move the damn wire. There is legitimately no way I can get that in there. Without like pulling other stuff out. For instance, I have to pull that out. Pull 13 out. Push it into the other pinhole. Run it. 14 back in. There, shouldn't have too much of a problem now. Ugh, that was horrible. It's actually kind of painful when you have to do that sort of shit. Okay. Yes. Tinker boy, let's go. All right. What's going in there? And honestly, this is gonna be a pain. So once again, go here, bring it, and then I'm gonna straighten that back out so I can push it through yet another underside of this. I'll try not to get it knocking out everything. There. Where's that going? Please tell me where that's going.
The chip select 1 pin. And chip select 1 is pin 24, so right to the left of chip select 2.
Okay, that's legit, just trim it down. This. And then strip it. And that'll go in. Yeah. That one's in. Don't tell me otherwise. Okay. Let me pull this one. Possibly. Done. Pulled it underneath. Okay. Easy. Cracking. Done. Crack-a-lackin'. We have some level of stuff there. Don't get me wrong. All this shit needs to be populated with shit from around here. Look at this fucking mess. What the fuck am I going to do with all that shit? I've somewhat neatened up so I have some access there and some access there. But there's no way that's going to be enough. I'm probably going to have to recut all new wires for some of this shit. And try and, like, tidy it up in some way. Because it is a thick bundle of plastic and insanity right now. Especially this thing here. I don't understand how his looks so much neater than mine. Like, it looks like I've got fucking double the amount of wires there. And I guarantee you,
That's that one right
now
there.
we just need to set
It's
A12
the address decode
to...
logic for the 6522. But then we've got some other stuff down here that we need to connect as well. So if we look at what we've got down here, we've obviously got all of the data lines.
Yeah,
But we also
data
have
lines.
the read-write signal and the clock signal, this feed.
Yeah. The read-writes and clock signal. This is going to have to wait. So let's drop by 10 seconds. Just say we've done that. And say 3210. Alright. I'm done for now. I can't do any more. Alright. So if we go here, we get rid of this. We go X, exit. Okay. If we kill that. Disconnect that. That's the... Get in the clock module. Don't know why there's weird light on me. It's because I got a torch shining in my face. No, there isn't. Okay, never mind. I was wrong. Okay. So, now, you also go in there, and you go in there. You go in here. I need to jump to. Where was my other? Oh, did I get rid of that? All right. Let me. Sorry, I'm gonna run straight. There we go. I keep my thing here in that, so it's no longer 1520, but it's 3210. 10. $32.10 part 2. Okay. Okay. There. Now I can get rid of that and face cam it. And so we are pretty much done. One last look at the project. Fucking mess. Brilliant. I fixed a little bit of a bouncing issue by sticking a capacitor there. And this is starting to get wired up. It's still missing all the data lines, which is all this shit up here. And the clock pin, which is this thing here. I'm going to need to come up with a better way of doing this. I may just run a cable all the way around. I don't know. I do know that he does plan on switching to this crystal. sooner or later. That's this thing here, which is gonna, I believe it goes down somewhere around here. And that's what that is. I'm probably going to still enable connection of the clock with just this wire, and just, I don't know, maybe have a switch to turn it on or off here. I don't think I care too much about debouncing, but yeah, you know, you got this switch here and all that sort of stuff that allows me to switch between both. As you can see, there's the thing, there's the blink, there's the thing, there's the thing. Done. Alright. This keeps falling out. It goes here. I hate the fact that it keeps falling out, but there's not really any reason, any way to stop it. These will be hooked up eventually, as well as my brilliant little LED thing. I remember what happens. I believe here was the LED screen or something, or was it here? I don't know. It was either here or here. I'm pretty sure they eventually put a clock there. Yeah, yada 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 yada. I still have this other chip. I don't know what it is. It's some sort of, I don't even know what fucking brand that is. But yeah, but there's another one here. There's one more chip here alongside the little crystal clock. It is exactly 1 megahertz. But yeah. Turn that away. Get rid of this stuff. Put this back up here. My little bit of core flute that I use as a background for it to make things easy to see, so that we're not like looking at my mouse pad. And I actually have a ton of core flute because I bought that core flute, right? But it came in a big fucking like gigantic signboard rectangle. Because it's technically, that's what it's meant for, signboard. So, you know, it's big plastic, big corrugated plastic sheet designed for signage. Most people glue shit to it and then hang it up outside or some bullshit. You know what? I'm using it for like backdrops and shit like that and whatever else. I was originally planning to glue shit to stick that stuff straight to it, but nah. I'm gonna run this. Just running the scanner cable so that it comes out the same place my power cable comes. There we go. Now if I ever need to write chips and shit like that, I have access to it. I'm just gonna stuff it in the side of my Stream Deck. There we go. Easy. Let's get rid of it. ROM programmer goes in with the rest of the kit stuff. That's where I put it to ensure more continuance. There we go. Okay. These tools just go underneath the monitor. I should connect this up to my desktop, that monitor, and then just have it like playing Gandalf or something while no one's looking. Problem is it's a TFT touchscreen, so it's probably it's TFT screen, which means it's kind of shit. It's a TN panel, sorry. It's kind of shit from shitty angles. I don't know how good it's actually gonna look here. Luckily, I have this desk cam thing there, and there we go. That goes back there, and with that, I don't think there's anyone on Twitch I can raid. Tuesday night, you know, it's a bit of a fucking shitto. Brobe is there. I could raid him. He's playing Minecraft. Hold on. Am I the only one in the science and tech? Or is there like having a laugh, live earthquakes, parents fly in at 5:30? Yeah, no, there's not a lot of stuff. There's computer repair. What the fuck? There's a flat earth channel? Oh, fuck off. They should be banned from going thing. I love it. It's actually labeled. They've actually tagged themselves as conspiracy. Fuck off. No, I'm not. There's no way I'm rating that. That's fucking stupid though. Oh man. Unless they're dissing Flat Earth. No. Yeah. Alright, you know what? I'm done. Okay. Catch you later. Yeah. I had a lot of fun tonight, and I need to go to bed. So, bye.